This recording should be better because I have reset my Zoom such that we actually have human beings and the presentation rather than only present. I dislike that very much. Um, okay, so now I can share. Why is it asking me? Uh, okay, well, I don't particularly care for this. I just want to share. Um, you can see, right?
Yes.
We are in slide 225. Yeah, that's the right spot. So this is just a sort of high-level summary of what we were doing, just to give you a perspective of things. Now, we are actually solving the Liouville equation, but the Liouville equation, if you recall, can also be equated to or mapped over, and this is the tricky part, only within the context of a canonical ensemble to this equation here, to the, uh, let me, to our uh, generalized Bourgeois equation, this equation here. So this is a very important point with regard to what I had asked you to do. So the Liouville equation itself doesn't have any temperature dependence. It doesn't have any ensemble dependence. Once you introduce an ensemble, uh, then you may have some additional uh, bonuses that you get on the original problem you're trying to solve. In this case, our original problem is the Liouville equation. But once we introduce the canonical ensemble, temperature, volume, fixed number of particles, then it turns out that we can cast the Liouville equation as a generalized Langevin equation. First point. Generalized Langevin equation is characterized by this little fellow here, which we call the memory function, which enters into the kernel. So Liouville equation is stated as a first order equation. This is also stated as a first order equation, excepting it's stated as a first order integral differential equation. This is the differential part, this is the integral. It looks benign, but it's a difficult equation. It's a difficult equation in terms of what it conveys. It's also a difficult equation in terms of how to understand the terms and calculate. So from both sides, unlike the Liouville equation, it is a difficult equation. However, Liouville equation cannot be directly solved excepting by short time expansion. Why? Because the solution of Liouville equation is trivial. E to the Liouville operator acting on A. And you can always expand the exponential with as many terms as you want. And at the end of the day, it's going to give you a time series. So it's going to be a perturbative time expansion, Taylor expansion, which we call a short time expansion. This, on the other hand, gives you a better proposition. You can certainly apply short time expansion, but this is an integral differential equation. It tells you that you have an equation. If you know the quantities involved, maybe you can get A of t directly without having to do the Liouville operator problem. Okay, so now the issue is our goal in the what I gave you is to calculate the memory function, the phi of t. Now, memory function in general is a tough quantity to calculate, and people in general don't know memory functions for most systems. Why? Because of the reason it's a tough quantity to calculate. People don't find memory functions as a matter of habit when they solve a problem. They are tired doing a relaxation function, let alone a memory function, which is an order removed. Not only that, there is another very difficult quantity, and that is this quote unquote generalized random force term. It's a bear of a problem. So even if this were to be killed off, which actually can be done if instead of calculating the problem for the operator A, I'm calculating the problem for the relaxation function only A0. In that case, you have A0 of t here, you have A0 of t prime here, and you have 0 here. In fact, we did that. So if you go back and look at the slides, you'll see that I actually did that. Anyway, so now the question is that when you are asked to calculate the memory function, what kind of quick and dirty stuff can you do? That's the question. So let us first step by step look at what tools we have. The first tool we used was that we wrote this A of t in a Hilbert space. And so we have to find A nu of t and we have to find F nu. So F nu first, A nu of t second. That's the first thing we have to do. So if we can solve for both of these, we can find A of t. We can find our solution to the problem. So that's a solution to the Liouville equation. That's also a solution to the generalized Langevin equation. For the generalized Langevin equation piece alone, we also have the generalized random force operator that we need to calculate. No problem with the F nu because F nu we have to find anyway, but there is a problem with this character B nu of t because this is a different thing now. And as luck would have it, phi is directly connected to B1 of t. Only B1. And observe that here nu starts from 0, but here nu starts from 1. So the first B is what takes you directly to the memory function up to a constant. So you know the thing well. We have selected for now a Hermitian dynamical variable. Hermitian dynamical variable allows us to write 3-term recurrence relations connecting the F's, where the delta nu is the ratio of length square of F nu over length square of F nu minus 1. And this is just nomenclature. F of minus 1 is 0 because F starts from 0. And delta of 0 is 0 also because delta starts from 1. So this is my RR1. So with RR1, I can construct my F nus. And if I know all the F nus, I know this part of the problem. If I know this part of the problem, I know a significant part of the A of t problem. And if I know F nu, I can also start constructing F of t, the generalized random force. So all of this you have to now hold in your head because these are very foreign to you in a way. But there are all these complicated relationships. First, the memory function itself, which is time and temperature dependent. And nobody else is time and temperature dependent in general, but this guy is, and eventually there may be some temperature dependence here which goes away. So that's another story. I'm not going there. But the focus is on finding A of t itself. And for A of t, however you calculate, you're solving Liouville equation, generalized Langevin equation, whatever you're solving, you have to go to the first recurrence relation formula, this version of it for Hermitian dynamical variable. Just to remind you, for non-Hermitian dynamical variable, the 4-term recurrence relations I showed you, that was in Hong's paper. Okay, now comes the next part of the problem. Now comes, this is actually very, very critical. There are two possible scenarios here. Let's use the red. At the simplest level, not in general. You see, delta nus, if you recall, in everything we did and you tried, F news become bigger and bigger as you go higher and higher. Unless you have a finite Hilbert space when catastrophically they cancel out and Hilbert space closes. That's very rare. So F news grow. And because delta news are F news square in the Hilbert space, length square in the Hilbert space, naturally delta news should grow. Now, the simplest possibility is that delta nu doesn't grow. It remains flat. By the way, I've never encountered a situation where delta nu goes down. Never. I don't know why, but I've never encountered one. But I think part of the reason is because when excitation spreads, it just involves more and more pieces of the problem. I tried to construct models where it will go down, but I have thus far been unsuccessful. So delta nu is constant. This is one case that will happen. And all these cases that we know of where it happens tend to be rather special. So for example, the harmonic oscillator problem, if you look at the work that we covered from Professor Yu's research, you will find that delta nus are typically fixed. They may have slight variation, but they don't grow, they're fixed. Number like half or 1/4 shows up. The other time that happened that we saw together was in the surface spin of the spin-off XY model at infinite temperature. Surface spin only, not the bulk spin or other subsurface spin, only surface spin gave the same result. And when delta nu becomes a constant, the relaxation function immediately becomes some kind of a Bessel function. So therefore, delta nu constant has a one-on-one relationship with a Bessel function relaxation. Whenever you see a Bessel function relaxation in any problem, you can pretty much blindly conclude without any risk that your delta nu, if you were to calculate, would be a constant. Big realization. However, the other option, if it's not a constant, is it keeps growing. And since it doesn't tend to go down, the question can be raised, can it flatten? Can it go up to a point and flatten? Thus far, I have not been able to find any case where actually it flattens. I don't know why, but I haven't been able to find. So my hunch is that there may be some specific models, but that's not a standard behavior, because when excitations tend to involve more and more pieces of the problem, particles, spins, whatever, it's an ever expanding proposition rather than something that gets controlled and stops growing. That can happen in disordered systems. So I'm keeping disordered systems out because they are difficult to handle. So the next growth that you can encounter would be ultimately, if not right away, ultimately a linear growth of delta nu. Linear growth of delta nu can be complicated. But if it were perfectly linear, 1, 2, 3, 4, perfectly linear, then you will rigorously get a Gaussian relaxation. Rigorous. However, what can happen is you can have a situation like this. Let's say this is nu and this is delta nu, and you can have them oscillate like that. So this would be like, let me take a black one here, make a fat one here. This is delta 1, delta 2, delta 3, delta 4. delta 5, delta 6, delta 7, delta 8, delta 9, delta 10, etc., etc., etc. Actually, I've tried to make a logarithmic plot rather than uh, a linear plot. So this is more like better to interpret this as uh, a log, and this also as a log. And then you can see the scaling pattern. Okay, so here you see, ultimately it's becoming linear. Ultimately it's becoming linear. So what happens? It's the question. Do you get a Gaussian? Do you get something different from a Gaussian? And this was a very important area to explore. And early on in my career, I explored this problem very carefully. Wrote quite a few papers on it, important papers as they became, luckily. But what turned out to be the case is that these early deltas, delta 1, the early delta oscillations. So if you think about this, it's oscillating about some line, maybe like this, like that. Not the best drawing, but some line. So this oscillation means what? Oscillation means some f news are bigger, the next is smaller, bigger, smaller, bigger, smaller, something like that's happening. So when the deltas are being calculated, deltas are picking up on these oscillations. And when that happens, when you put them in the continued fraction, because remember, ultimately you're putting all the deltas into A0 of z, right? So your A0 of z, A0 of z, so this is what? This is 1 over z plus delta 1 divided by z plus delta 2, etc., right? Dot, dot, dot. So these deltas are entering there. And always remember, you can do a little bit of fooling around and you'll immediately see that the lower deltas play a big role in A0 of z. The deeper deltas, they play a big role, but in terms of setting the pattern. But the lower deltas play a very important role in setting what kind of relaxation you will get. So Gaussian is like this. If you have oscillatory deltas, typically what happens is you start to get all kinds of complicated oscillations, but on what may be an overall Gaussian type decay. So now your A0 of t may typically look like this. Let's try to draw it. It can typically look like so this is your t, and this is your A0 of t. Or it can be some other complicated thing. Okay. So this oscillatory behavior is a very common behavior, and I think some of that oscillatory behavior may actually be there the moment you switch around the transverse field magnitude and the magnitude of the J in the transversizing model. Remember that only when J and the field coefficient H are exactly equal, you get a linear pattern. But if J and H are not exactly equal, you start to get a complex pattern, and that complex pattern actually has oscillations all the way with an overall linear trend. All right. So that's what we were trying to do, and that's what I want you to finish properly. So, so you see, you can now find A0 of t once you know the deltas. Acha, there are some things you have to be very careful about. People back in the 70s, after Modi did this work and Dupuy's papers came out, they wanted to deal with this infinite continued fraction because they had to calculate this. And one of the common things that was introduced was called an n-pole approximation. N-pole. N-pole meaning there are two z's here, so this is basically quadratic. So it will be quadratic downstairs with a linear z on the top if we just truncate this. So n-pole would be basically z to the n in the denominator. That will be n-poles. All right. However, people quickly realized that these n-pole approximations were completely unreliable. And the next attempt that was made was, instead of just cutting it off, people said, okay, we won't cut it off, but we would just stick some kind of a function in there that doesn't cause such catastrophic end to the infinite fraction, but just kind of gives it an overall feature. So they introduced something called the truncation function. We'll come up with all these beautiful names. Truncation function. Truncation function can be like you got 2 or 3 deltas, and then you stick in some Gaussian function or some function that makes sense. There is no justification for it. But you got to try somewhere, so you try, right? That's what people tried. Well, when you try things, 99% of the time in physics, you fail. So they failed, as predicted. so, so that first the n-pole approximation failed, second the truncation failed. This is around the time when I had finished my PhD, and I was thinking that, well, I now want to do different problems because I'm a postdoc, but my postdoc advisor gave me a lot of freedom. He said, Surajit, 50% of your time is on our work, and 50% of time is yours. You do whatever research you want. Nowadays, nobody would give you that freedom, but back in 1989-90, I got lucky. So, and what was even nicer was my postdoctoral advisor himself got interested in my other problem, which is one of them was this problem. Since I finished in 89, all these papers were written when I was with him, 1991, 92, 93. 93, I came to Buffalo. Anyway, so long story short, I decided that I was going to try out these various ways of calculating A0 of Z without truncating. Professor Mohanty, who was my advisor, postdoctoral advisor, he was a brilliant physicist, actually, theorist. He's turned 80 a few months ago. He said that this truncation thing doesn't work. He said, I had tried it many, many years ago in the 70s myself. It doesn't work. So you better find a new way. I said, cool, I'll find a new way. So I decided that why the hell should I truncate? Let me just, instead of truncating at a few levels, let me truncate at 100,000 levels and truncate again at 100,001 levels for 2 runs. So I did some of those studies with one of actually the PhD students in the group who was a fantastic programmer. And what happened was that we found that when there is linear growth, constant was not a problem. We could solve it analytically. This case, you have seen that. Basically, we just replace the rest of it by the same continued fact. That's A0 of Z plus delta 1 divided by Z plus A0 of Z kind of a thing. Because the same thing repeats itself. So you can stick it in. So in this one, linear growth one, we found that we could approximate by 10,000 levels, 10,001 levels. Works beautifully. You get almost the exact result. So that was a breakthrough. And this led up to a paper we wrote in Physical Review Letters in 1992. and we called it something like dynamical convergence method or something. And it was extremely successful. And that is the code I sent you, that original little code. And you have to use that, otherwise you won't be able to get the right result. So what happens now was somebody told me, I think my advisor probably, not my postdoctoral advisor, my PhD advisor, had mentioned that if this nu grows faster than linear, can your method work? I had a hunch it might not. So I tried and I failed miserably because forget about 100,000, 100,001 truncations. I truncated at 1,000,000 and 1,000,001, and I found that the results of 1,000,000 and 1,000,001 had nothing to do with each other. There was no convergence at all. Zilch. So after 1992, the next paper we published on that problem was in 2018 or 19. That's how long it took me to solve that problem. And even now, it is not solved to probably utmost satisfaction. It's solved to some satisfaction. It's like having you taste the ice cream and not quite eat it. Now, okay, so the long and short of this part of the story, therefore, is that A0 of t calculation is generally very challenging, but using the dynamical convergence method, which is the code I gave you, you can do it very well, provided the convergence is good. And good convergence essentially means that if I write delta nu as nu to the power phi, this phi must be less than or equal to 1. Then it works very well. That means linear growth. Delta nu goes as nu to the phi. However, if delta nu goes as nu to the phi where phi is more than 1, you are doomed to fail. It won't work. There is no convergence. However, there are physical problems where this happens, where phi is more than 1. So I won't tell you that now. The reason why I said this background detail is because what I wanted you to do in that problem is to calculate the phi of z first. And phi of z is same as A0 of z, excepting it starts from 1 over z plus delta 2 over z, not delta 1 over z. The most important first level is gone. But you know all the deltas, excepting that you cannot take delta 1 in your study. Because if you look at the formula for phi of z that I gave in the discussions, actually I didn't, I think I gave it in the discussion. I know where it is. It's not in the original discussions, but it's part of the paper. Part of the spin paper, I think. It's still before that. Now, this is the bulk spin. You see, this is linear growth, as you can see. Delta nu is nu delta. Somewhere around here in the around here somewhere in the 50s, 57 or something. Ah, there you go. I think this may be it. See, this is 5. You see that? And I gave b mu of z. And b1 of z is what phi is. So it starts from delta 2. So all you have to do is take the code, plug in from delta 2, and then once you go maybe 8, 10 levels down, you can then insert a general formula where the code will calculate the next delta, because delta nu is some constant times nu. So you have to give, and then you have to set the number of levels. So you can set 10,000 levels. Then you can check with 10,001 levels. And as long as your result is coming out just right, that means you have reached convergence. That's what I wanted you to do. So go back to the code, pull it out, and insert that. Insert that delta 2 onward, no delta 1. And insert the extrapolation for delta nu. How will the program calculate what other delta nus you need? The moment you do that, you'll get the perfect result for memory function. This was the place where I thought that both of you were not very clear. So that was the reason why I did what I did right now. Okay. Do you have questions?
Yes. So can you go to the slide where you show how the memory function should look like?
Here, this one?
Yeah, the next slide.
Huh.
Yeah, so you draw this, right? So this oscillation should go below that timeline. So x-axis basically here.
It can.
It can.
A0 of t can be positive and negative. But one of the things that you have to, I'm glad you asked this question because I forgot to say something. In a Hermitian A, dynamical variable problem, at temperature going to infinity, so beta going to 0, your A0 of t will always be real. When you turn on beta, then your A0 of t in general can be complex. And the reason why that is okay is because A0 of t is not an observable. In fact, this is the source of why condensed matter physics is so difficult, in my opinion. Because A0 of t, if it were an observable, you could just go to the lab, you can measure A0 of t, you can compare the two, and there's no problem. However, nature has decided that it will make the Fourier transform of A0 of t into an observable. So, in other words, A0 of omega is an observable. And that can be directly experimentally measured, which is what I had mentioned is called the dynamical structure factor. You usually measure it with neutron scattering typically, but you might be able to get away with X-ray scattering or electron scattering or what have you. But normally it's neutron scattering because they're uncharged particles. They don't respond to the presence of charges so much. You shoot neutrons, neutrons scatter off. You can calculate the S of k omega. And that S of k omega, if you integrate over k, you get S of omega. That is same as A0 of omega. So A0 can be complex, but A0 star will be real, and that is your S of k omega. Fourier transform is the type. So yes, short answer to your question is A0 can be quite weird. In fact, I don't know if you remember, but I'll show you when I did this study with you guys, the non-Hermitian study. See, A0 of t already was complex. See that? I beta. But when beta is 0, that term drops off. It is a well-behaved Bessel function. So yes, it can be complex. But of course, it doesn't matter because if you do scattering problem, this thing will come out to be S of k and omega, which is real. Because then it will be a mod square of this thing. So if you call this A0, A0 star will come. You multiply J0 of t plus I beta over 4 J1 of t whole square with half J0 of t minus I beta over 4. You'll basically get a real function. So that's the problem. Okay. Any other questions? Yes.
Yeah, so because I tried to plot it
Yeah, I
and
saw that.
so another try, I tried it again, and
Uh-huh.
it is simple like Gaussian decay, but there is
Okay.
no negative part.
If it's a pure Gaussian decay with just 1, 2, 3, 4, 5, 6, there will be no negative.
Okay. And
The negative
uh,
part will come typically when there are oscillations in
okay,
the deltas.
okay. And
You are right about it.
okay. So the paper that I was actually tried to follow, I haven't studied entirely, but the your paper in 1992 in physical letters, long time dynamics via
Yes,
direct
yes.
summation of infinite, and there is
Infinity.
this plot of Gaussian decay,
Yes.
and there is a small, very small part going into the negative, and then it's just
That is
uh,
because that one may not have been perfectly linear, that case.
okay,
It must be that.
okay,
Because I don't remember what we studied in that one. That one, we had taken several cases because we had discussed in detail what happens when there are oscillations and so on. I think that must be tied to that. Tony, did you have any questions?
Just an overall clarification. So I made a bunch of plots of A0,
Yeah,
but so you want plots of phi of Z instead, which is close to what A0 is, but it just starts from delta 2 instead of delta 1.
correct. Correct. Yeah, yeah, yeah. That's the
Okay,
main
I can,
difference. And you
yeah,
have to
okay.
multiply that with delta 1, right? Because if you go back to,
Mhm.
I think, slide 57 here. So it's delta 1 B1 of t. So you do B1 of Z, then you do an inverse Laplace transform and come to B1 of t. In fact, that
Okay,
inverse Laplace transform is also part of that code, I think.
okay,
So then you do B1 of t and then you multiply B1 of t with delta 1.
okay.
And that should give you the actual correct memory function. That's how it works. Okay. So today
So I
this
guess
was,
what's the physical difference between A0 and 5T?
they're actually quite different because of the culprit being delta 1. That's why I made the comment that the highest levels of the continued fraction, the worst culprits in dictating what comes out on the other side.
Hmm.
So unless all the deltas, unless the first two deltas are the same or something, which is almost never the case, it can actually be quite different behaviorally.
Okay.
And this is also the reason why memory function is actually harder to uh, easily mimic with a well-known function because it is a messy function almost always. And chemists who study various kinds of solutions of this chemical, that chemical, they are often the ones who are very interested in getting the memory function as a package that they can stick into some other problem. So they are the ones who started this n-pole approximation, truncation function. Half of these games were started by the chemists, physical chemists. So if you go to Journal of Chemical Physics in the 1970s, you will find every few papers people were doing something on this problem. Okay, so the history is fascinating. So they figured out that, God damn it, they couldn't find a proper memory function. And essentially, chemists gave up on it. And they're very sore about it. So there used to be a very famous guy doing this kind of work from Washington University in St. Louis, Polish last name. So when I was studying this problem, I actually studied one of his papers and I found that his consideration of the memory function was not really an admissible function. It couldn't be constructed easily. So I wrote a short paper as a comment to that paper. Now, this Washington University professor was a very powerful chemist, a lot of clout. And the editor of Journal of Chemical Physics at the time was a University of Chicago guy called John Light, John C. Light, J.C. Light, very well-known person. J.C. Light and these two guys were very close friends. But J.C. Light was the editor. I naturally wrote the letter to the editor and said that, look, this is a very interesting paper, but this is a problem with the paper. And if you fix the memory function here, you can get a better result. This was the rudest rejection I got because I got a letter from John Light within a week saying that your paper seems irrelevant to our journal. It is being declined. It was most relevant to that paper, but he was protecting, sadly, his friend who had made a mistake in the paper. Anyway, I didn't go back and pick a fight with him. I figured that I'm just starting my career. This would be a natural way to commit suicide before it all begins. So I shut up and realized that I had stepped on the wrong dead body here. So I just anyway. So okay, let me now go back to another thing that I wanted to point out today. And this was in the stochastic problem end. So you may recall that we talked about the Chapman-Kolmogorov problem. We came to the master equation problem. And then we focused on the W matrix and the eigenvalues of the W matrix. We looked at Gershgorin's theorem, all of that. And that was essentially a significant part of what we did over the last few weeks. So all of that you may recall. And we talked about this eigenvalues being cannot be real and all of that. Anyway, so now what happened was that we took then we talked about these dichotomous system, and we showed that you can calculate the lifetimes in each state and the rates of transition, and all of these problems can be nicely done. So we kind of did that too. And then I slowly moved over and transitioned to the random problem. And here we had a problem, right? Remember that? Okay. So actually I discovered that the problem was created by AI because AI flipped the arrows without letting me know. See, this arrow was drawn as going from hamburger to pizza, but actually it's pizza to hamburger. And the hamburger to pizza is 0.6. So these two arrows were flipped, which I have completed with in black here. And simultaneously, these two arrows were also flipped. So now you see 0.5, 0.5, it works out.
Yeah.
So hot dog transition is fine. Hamburger transition 0.2, 0.2, 0.4, and 0.4, 0.6 is 1. And pizza transition is 0.7 and 0.3. So everybody is happy. And this problem, I don't remember for the life of me where I picked this problem from, because it was not from Balkrishnan's book. It must have been from some other place. But this problem has another problem. So this problem, therefore, naturally, because of this diagram here, you can set up one of these transition matrices. A transition matrix which is 3 by 3 means that if you are trying to diagonalize it, it should have 3 roots. Now, the way the math works is that you have the transition matrix and you apply some initial choice, which is a row vector, which is your P. In this case, P is 0.35, 0.21, 0.43, for example. You take this P and apply it with the transition matrix and you get a P prime, right? Then you take the P prime and apply the transition matrix to it, and so on and so forth. That's how we keep doing it. So one thing that, so here it is. So P0, for example, is 0, 1, 0. P0 times the transition matrix gives you 0.30, 0.7. So you see the numbers have changed. And the exclusion that it can't have 1 again has come in. Then P1A is 0.30, 0.7, again multiply. That gives you P2, and so on and so forth. So if you do this forever, then you should get to some kind of a stable P, which we call P stationary. And of course, normally you would do it numerically. But if it is a stationary state, you can think about this as P stationary times A should give you back P stationary. So you can think of this as P stationary minus 1, the whole thing times A is equal to 0 at steady state. If you do that, then you should be able to find the stationary states by finding the eigenvalues of the P stationary matrix. And that's where I found there is another problem, because there is an additional constraint that the 3 probabilities must add up to 1. And they do. In these cases, they do. But when I tried to do it manually, I found that that doesn't quite work because it's a 3 by 3 matrix. It's basically a cubic equation. I haven't been able to solve this problem. So if you can solve it, I'll be interested. So if it's a cubic equation will have 3 roots. And sure enough, 3 roots should be P1, P2, P3. Because those are the only things that can satisfy the condition that P stationary minus 1 is equal to 0. Now it turns out that either I'm making a mistake or I don't know what I'm doing, but a cubic equation can have 3 roots in general when A, the 3 roots converge to 1 root, or B, you have 2 imaginary roots and 1 real root. Now, probability can't be imaginary. So there is no way I can find 3 distinct real numbers that will come as a solution to P stationary out of this. So either I am making a mistake somewhere, or this problem has not been set up with the correct transition matrices. Either way, this problem has a problem. But I was thinking that the fact that this problem has a problem is a good thing for us, because it gave us an opportunity to think a little bit harder about this problem and figure out that this problem has a problem, which we otherwise wouldn't have seen. In fact, the first time I did this, I didn't notice it. And then I said, wait a minute, let me work it out by hand. And the moment I started doing it, it became pretty darn obvious that there is a problem. Yet I can see iterating. So my compromise is that it never goes to a stationary state. It probably comes near some kind of a correct answer, and then it starts to oscillate. So the moment you start to force it to come to a stationary state, the problem becomes unphysical. It reaches some kind of a state which is a semi-stable state, and that's it. So the fact that, but I don't know for the life of me why it doesn't work. I would love to understand why it doesn't work, but I couldn't figure it out. I spent time on it, but really not enough. Okay, so we don't have a whole lot of time, but let me spend a few minutes today uh, trying to talk about, you know, stochastic processes as such, but stochastic processes have limitations. And when I learned about stochastic processes, I always thought it was a very cool thing to do, and I had a nagging level of discomfort as to I'm impressed with it, but I don't like it. And I couldn't tell you why. I'm impressed with it because, it clearly pulls out so many things out of the hat that otherwise would not have been doable using sheer power of math that is impressive. But I was uncomfortable with it because deep down I knew that not all stochastic systems I can think of can be captured with it. And that was the purpose of me showing you this picture, because there's absolutely no way on earth any stochastic model will be able to predict what happened here. Which brings us back to the predictability of stochastics. So stochastics have to operate within the bounds of predictability. Something can be completely unpredictable and stochastics wouldn't operate. But something may be, guessable, and then stochastic can operate. So that's one thing I want to point out today, because it is a joke, but at the same time, it's not a joke, because things can be so random that your ability to predict can actually fail because it is not predictable anymore. So my own forays, and of course, if I did something primarily on my own, I'm happy to share it because I can share the most insights on that, right? Because I was actually part of that problem, and it's a part of what we are studying. So naturally, I thought that I should tell you a little bit more about the battle problem that we studied in the early part of the 21st century, so to speak. So we started around 2004, and we carried on for about 15 years on this problem, off and on, off and on. So the so-called simplest part of the problem is actually the pure stochastic problem, which is this non-strategic. Non-strategic means it's purely random. That's what non-strategic means. Two-party battles. So just so that you know, we did the strategic problem first. And I had no intention of doing the non-strategic problem until, as I said, Linda came along to do her PhD, and she wanted to try it. And I said, fine, go ahead, do what you want to do. But my interest was in solving the Iraq War troop deployment problem. That was my original intent. And this was also the time when there were a chain of terroristic incidents. So I wanted to see if the model can be employed to study terrorism problems, especially the kind of terrorism that happened in the Taj Hotel. Which year was it, Vivek? Do you remember? 2008 or 2011 or something?
11, 9/11.
11.
Oh, sorry. Uh,
Around that time frame it happened. Let me check.
in 26/11. So
26/11. Yeah. So Taj Hotel at 26/11 attack. Which year? Date. It was 2008. Okay. So
yeah,
it was around the time when we were doing this. So this was a Tony, you may not know this one, but it was a really vicious attack lodged by Pakistani terrorists in the Taj Hotel in Bombay, which is one of the very, very high-end hotels in Bombay, and it's a historical structure actually. And a lot of people died, including many of the terrorists, and the rest were hung. So anyway, so going back to my screen, here we are. So we also wanted to study terrorism problems, which we did. I won't talk about that, but we wrote a paper on that problem also. Now, so this is like a summary of what Linda was thinking. I had kind of given her the outline that you have a conflict, and modern conflicts are very different from ancient conflicts. For example, Alexander the Great, traveled east. He came to Iran, he came to India, and along the way he stopped by in Central Asia, what are Central Asian countries. And Alexander the Great actually, one of his missions was to expand the territory of the Greek Empire. So clearly, there was that part. Old battles were more about territorial expansion. Modern battles are more about more strategic because they want to typically attain some milestone that is important to attain. For example, purportedly Iraq War happened because Dick Cheney gave the wrong information that they had weapons of mass destruction. They did not have, as was later found, and that was the pretext for the war to destroy the weapons of mass destruction. Same is going on in Iran. It's always the same game that the West plays, unfortunately. Anyway, so that was a strategic war because the war had a goal. They were not interested in capturing Iraq and making Iraq a part of America. No, that was not part of the plan. Okay. Part of the plan was to see if the weapons of mass destruction were there, or at least that was the pretext of the plan. The real plan was to get rid of Saddam Hussein, which made things worse, obviously. Instead of having a controlled fire, you have an uncontrolled fire. Typical American foreign strategy in faraway places. Anyway, that's another issue. But these are strategic battles, and in strategic battles, it is the strategy that should dictate who wins. And historically, the armies that have been more successful than others in modern times across the world are the armies that have had good strategies to pursue wars, always strategy based. So that's what I wanted to study. So I'll first tell you just a little bit about what Linda did that was non-strategic. Non-strategic meaning people are just fighting a war in which there are different parties with different levels of ammunition. Both of them are equally lethal, so they are equal. And then this is kind of a moot problem because you would expect that the ones which have more fighters on the field will do better. What else can happen? And you guessed it, that is the answer. Okay. That's why I was not interested in this problem, but Linda was very interested. I said, okay, fine, you do it. I have no problem. So this is the battlefield. There were 5x5 lattice. And here, S plus and S minus, this is Linda's language, are the strengths of the soldiers. So let's say +1, +2 to +A. So let's say A is equal to 1. So +1 is for side A and -1 is for side B. The idea is that if a +1 attacks -1, they'll both at least hurt each other on average, which means +1 and -1 will cancel out to a 0. So they'll both become ineffective. That was the logic. It's trivial. Okay, nothing, no high-flying physics or logic here. Trivial. You have a big gun, I have a big gun, I shoot you, you shoot me, we are both dead, nothing happens. That's the picture. So, okay. And then, of course, EA and EBs are how much of the lattice each species is occupying. So EA can be one, that means the entire lattice is occupied by a species. That's not the case. We typically say, usually a territory is a large territory. You can have 10%, 15%, 20% of the territory where you have parked your soldiers to guard the territory. That's how it goes. So here the negatives are the attackers and the positives are the defenders. So you can see lots of attackers here after some iterations. And the blue ones are the positives and the pink ones are the negatives. This is the same picture, but here it's a sort of contour plot. Not a contour plot, it's a roughness plot. Positive, negative. The number -11 typically would come if you keep throwing a fixed number of soldiers in every iteration on the sites. So after maybe 30, 40, 50 iterations, some places will have a lot of type A soldiers, some places may have some type B soldiers or more type B soldiers. Here you can see the type B soldiers are being killed off because the numbers here are far less and type A soldiers are more. So they may have bigger numbers or the other way around. In this case, it turns out that I forgot what B is. B is negative. There are more negatives. Say B is a little bigger, 0.55. A is a little smaller, 0.5. That means 55% of the lattice is occupied by B, 50% by A. Okay, and B is the negative ones here. So therefore, there are more negatives here because of that extra 5%. That's what you're seeing. It's as simple as that. So in other words, a 5% difference in troop deployment in a random battle is a lot. That's what you're also seeing. And Linda basically did something that we just discussed right now. So he had this P matrix, which is the row matrix, which gives you detail about how they have been deployed in the various sites. And this D matrix is the equivalent of what was the transition matrix there. So you can see here, D matrix is the vector of the probabilities. And this P matrix, big P matrix, is actually the transition matrix. So what you'll do is you'll have an initial D1 matrix with and D1 matrix times P12 will give you something. Then you will apply the next P matrix, which is not going to be the same as this P matrix because now the battlefield has new people in the new time step. So instead of having the same P matrix every time, here the P matrix itself also iterates in every step. So the P matrix is a time-dependent matrix that is evolving with every time step, and you are deploying troops. So both are changing. So it's a little bit more complicated, but it can be done, and she did it, and this was being done numerically. Then she tried to do it on a large scale also numerically and then analytically, and more or less managed to do some calculations which were reasonable. These are some of her formulas. No point to go there. It's mostly by inspection they can be pulled out. This is sort of what happens. The probability density of how many soldiers ended up on the sites essentially went according to some distribution. Some sites had a lot of soldiers, some sites had less soldiers, and this is what it shows you. It's pretty even this way or that way. It's not symmetric because one side has a little bit more than the other. For example, A side has 60% of lattice sites occupied, and B site has 50%. So naturally, the A site will have a little bit more of a skew. And because the B site had less, B site is decaying out in terms of numbers. probability of finding species B ultimately goes to 0. That's what this part of the problem is. So anyway, so this is the part of the problem I'm going to close with, because on Thursday, I want to show you that the same probability-based idea, but now with strategy, actually takes you to some really incredible predictions. So I'm taking the opportunity of doing a bit of stochastics to give you an idea of a new problem, but at the same time, hopefully taking you to how you can make a relatively simple, benign extension of this problem to a territory which is non-stochastic. And it becomes an unsolved problem of a real battle. And this is the fun of doing this kind of modeling, because you can, with a little bit of thinking and creativity, you can take a very mundane, benign, everyday problem and you can make it into absolutely cutting edge science, policy, science, whatever it is that you wish. That is the purpose behind why I'm doing this. So I'm going to tell you the background first on Thursday. And the background was the political background that mattered at the time. The political background was that, as I said, Cheney declared there are weapons of mass destruction. So that was backed up by George Bush. Then at the time, the defense secretary was Robert Gates, who was a very effective defense secretary. And Gates and General Colin Powell, who has now passed away, were the people who essentially strategized the war. Colin Powell was the Army Chief of Staff, if I'm not mistaken. And this led up to the battle strategy that was followed against them. And what I also want to point out on Thursday is how confused this battle really was. They wanted to get Osama bin Laden. They wanted to get Iraq. Osama bin Laden was not in Iraq. Osama bin Laden was sitting in Pakistan. Americans thought he was sitting in Afghanistan. So they went over to Afghanistan. I mean, they made a mess of the battle, right? So if you want to make a mess of a battle, how you want to make it, you will see in this war. Here, at least they did something. In Iran, oh my God, I just think America is not going to exist after a while, because economically will be finished. But this battle also was economically very, very bad for us. Anyway, so let me not tell you the full story, but I'll lay down the story and I'll lay down how you can actually model it on a computer. I mean, it is almost semi-trivial, okay? You don't really need to know anything about battles to model a battle. It is almost that dumb at the end of the day. Although, the army people, Navy people, Air Force people would make you think otherwise. They're the geniuses. Yeah, they're the geniuses fighting, but it's actually a relatively predictable problem. All right, let me finish here because there's a candidate today, so I want to go and listen to this guy's talk. We'll continue on Thursday. Try to finish this memory function study. I'll give you guys something else, which is now more tied to what you're doing, hopefully, so that way it'll be a little bit of a doable thing for you guys. Okay, let me close, and I'll see you Thursday, okay? All right, bye-bye.